Let's talk about properties. Properties are characteristics, and they come in several categories. We have physical properties. Physical properties are those that we can measure without changing the basic identity of the substance. So a physical property would be something like the boiling point, the temperature at which, let's say, water boils. And I'll use water over and over again because it's something you're very familiar with. And it's easy to imagine a pot of boiling water. Well, when we boil water, you have a liquid and the particles are just sloshing around each other. And as we start boiling the water, we move the molecules further and further apart from each other until they fly apart and vaporize. And so boiling point, the temperature at which water boils, is a physical property. That would be true of the melting point as well. And you could go in the other direction where you go from vaporized water and you condense it into liquid water, and then you can continue to extract heat from it, lower the temperature until you freeze it. Okay, so all phase changes are physical properties, those that you can measure without changing the chemical identity of the substance. Chemical properties, on the other hand, always change the substance from one thing into another. I could take, let's say, methane, CH4, I can combine it with oxygen, and if I wanted to measure the chemical property of combustion of methane, I would be changing it into CO2 and water. These are two completely different substances with what I started out with. So measuring the combustion or flammability or thermodynamic yield of methane is measuring a chemical property. You start out with one type of substance and you wind up with a different substance after the reaction is complete. And that is changing its chemical identity. It describes the way a substance may change or react to form another substance. Here is glucose, and you're doing this right now. This is technically what we call a combustion reaction. This is metabolism. You're taking glucose and you are reacting it with oxygen, and you're forming carbon dioxide and water in these ratios. So glucose and oxygen are very different from carbon dioxide and water. Continuing with properties, we have intensive properties. Intensive properties are characteristics of substances whose values don't depend on the amount of the materials that we examine. So, for instance, the color of a substance. I could have a gram of gold or a pound of gold. Gold tends to have this yellow color. And so the color of gold is the same whether we're talking about a gram of the stuff or we're talking about a pound of the stuff. Pound of gold sounds pretty nice. Intensive properties, characteristics of substances whose values do not depend on the amount of material chosen. Let's see, what else could I choose? We've talked about density when we were earlier in the previous lecture, and density is a ratio of mass divided by volume. And so density is definitely an intensive property. If I have 1 gram of gold, it will have the same density as if I have 1 kilogram of gold. And a kilogram is just 1,000 grams, which we will learn. So as I go from 1 gram, I'm going to go ahead and use a unit called cubic centimeters, which we will get to in a little bit. The ratio of grams, the ratio of grams to the number of cubic centimeters is what we call the density. If I take 1 kilogram of gold, what it's going to do is I'm going to have the same ratio. I'm going to have the same density that I did if I had 1 gram of gold, because the volume will increase as the mass increases. And so density is definitely an intensive property. Extensive properties are precisely the opposite of that. These are characteristics of substances whose values do depend on the amount of material substance. And I'm going to go back and we're going to take a look at density with respect to mass and volume. Now, as I increase the mass of the gold that I was talking about from 1 gram to 1 kilogram, which is 1,000 times greater, I also increase the volume of the gold proportionately, so that I wound up with the same density no matter what the mass was. So mass does depend on the amount. And one of the things that changed when I changed the mass was the volume. So the volume also depends on the amount. And so any property that changes with the amount is what we call an extensive property. Mass and volume are very much extensive properties. Length would be an extensive property. One that most people don't think about, thermodynamic yield, or the amount of energy that's released when you burn something. If I have a gallon of gasoline and I burn it, I get a certain amount of heat that's released. If I have 10 gallons of gasoline, I get 10 times the amount of heat that will be released. Or I can do a combination of work and creation and production of heat by putting that gas in my car and do some work as well. So extensive properties definitely depend on the amount. Intensive properties do not. Changes in substances, physical changes. These are changes in the physical appearance of a substance, but not its basic identity. That would include all phase changes. So if I boil water, that is a physical change because it's still H2O as boiled, as vaporized water, as liquid water, as solid water, which we call ice. And chemical changes, as we've said before, these are changes where a substance is transformed into something that is chemically different than the original substance that you began with. So keep it straight. Physical doesn't change the identity. Chemical changes do change the identity of the substance. Combinations of substances. We have mixtures of 2 or more substances in which each substance retains its own chemical identity. If I dissolve sugar in water, there are dissolved sugar molecules in the water. It's still sugar. It's still water. If I remove the water, you will have sugar in the bottom of your container. You're breathing a mixture of gases. You're breathing nitrogen, about 78% of the mixture, and about 21% oxygen. There's also some carbon dioxide in there, about 0.03%. And trace gases are also in those mixtures. And they retain their unique chemical identity that doesn't change when you combine them. That's what we call a mixture. And nature is a mixture of different substances that are in the same volume of space, but they have their own unique chemical identity. And a great deal of what chemists do in the laboratory is they separate the components of mixtures in order to examine one of those components. So if I wanted to examine in a solution, in a what we call a homogeneous mixture, that's uniform throughout, and there was only one substance in that mixture, I would use methods of separating the components of those mixtures to examine that one component. It's a lot of what chemists do. Okay? Homogeneous mixtures, uniform throughout the bulk of the mixture. It tends to appear uniform. If I dissolve sugar into water and it completely dissolves, you can't actually tell that there's sugar in there because it really just looks like water. Now, if I put sand in water, the sand doesn't dissolve in the water. They're completely incompatible in terms of solubility. So the sand will just sit on the bottom. It's still a mixture, but it's a heterogeneous mixture because the two phases are different. It is not uniform throughout the bulk of the mixture. Another example of a heterogeneous mixture might be your typical oil, vinegar, and spices salad dressing. And what do you do before you put the salad dressing on your salad? You shake it up so that you get a fairly even distribution of all the components of the mixture, but it is definitely heterogeneous. If all the substances in the mixture are in the same phase, it would be homogeneous, and it's uniform throughout the bulk of the mixture. So air, you're breathing air, which is 78% nitrogen, 21% oxygen. No matter where I take my air sample, that proportionality is the same, and that's uniform throughout the bulk of the mixture. Types of mixtures, as we said, homogeneous, characterized by being uniform throughout the sample. Here are some examples. Air, salt water. I'm not talking about seawater, which has fish in it, typically, and seaweed and sand and all sorts of things. But if I just dissolve some salt in water, scotch in water, if there's no ice, you have yourself a homogeneous mixture. Brass is a solid solution of two metals that are mixed together, but they still retain their own unique properties. Each component of that mixture, less than pure gold. And most of the gold that, or really all the gold that you have as jewelry, is less than pure gold, because nature really loves mixtures and hates purity. It just doesn't tend to make pure substances. It mixes everything up. Heterogeneous mixtures, things characterized by not having the same composition, properties, appearance throughout. Sand and water. Wood is a solid heterogeneous mixture. Oil and water, as in your salad dressing, those two do not mix together. Okay? If you let the salad dressing settle, you're going to see the oil on top because it's less dense, and we said earlier in the earlier lecture that less dense substances will float on more dense substances, and water is more dense than oil, and so the oil will float on top. Think about oil spills. In my day, the Exxon Valdez was a big tanker of oil up in Alaska that crashed on some rocks and spilled vast amounts of oil, which floats on the surface and forms globules of oil that tend to stick together, and it interferes with wildlife and the whole ecosystem. That's bad. Separating mixtures, which is a big part of laboratory chemists' work, trying to separate those mixtures so you can work with pure substances. You do filtration every time you make a cup of coffee with coffee grounds. You take the coffee grounds and you put them in essentially a coffee filter, and then you pour hot water in there. You actually do another type of separation. You do extraction. You're extracting caffeine and that luscious brown color and flavor and wonderful aroma of the components of coffee. That's filtration. Filtration, by the way, is really good at separating heterogeneous mixtures. Distillation. Distillation is something that we talk a lot about. Water is actually the most valuable substance on the planet, that is fresh water. And so ships have to use a desalinization process where they remove the salt from water. And essentially what you do is you boil the mixture of salt and water. The water vaporizes, the salt doesn't, and then you condense the pure water, and that's how you make fresh water. Distillation is a process used for separating the components of homogeneous mixtures. It's also used in the production of spirits in the liquor industry. Chromatography is another method of separation. We won't deal with it in this course, but you are separating based on polarity. There's a particular technique. You have a stationary phase, a mobile phase, and you're separating the components of a mixture based on that. If you take organic chemistry, you will do several types of chromatography: thin layer chromatography, paper chromatography, column chromatography, and you'll become very acquainted with chromatography. We'll focus on filtration and distillation. So here's simple filtration. You've got a simple filter. Here is your heterogeneous mixture. That's what filtration is good at, separating the components of heterogeneous mixture. And so you pour your mixture of orange and whatever the liquid is in here. The orange is filtered out and the pure liquid falls through the filter. This is a method called gravity filtration, and you will learn about that in your laboratory experience. This is a distillation apparatus used for separating the components of a homogeneous mixture. Presumably this is salt water. In this particular depiction, this is the boiling flask. We add energy, the water vaporizes, the salt stays down here in the boiling flask, and then as the water vapor rises, it enters a condenser. This is just like a radiator in your car. We're going to run cold water, and there's an outer and inner space in this condenser unit, and the cold water that you run up is in the outer portion of the condenser, and heat is extracted from the vapor. And remember, we talked about this in phase changes. As you slow the water molecules down, they get closer and closer together and they condense into a liquid. Now they're a liquid, they're connected and making and breaking connections with each other, and we collect in the condenser, we condense in the condenser, and then we collect in the receiving flask down here the pure water. This is desalinization, as I described, and this is done on ships every day.